Good evening, everyone. This is the 10th live problem solution session for the Aqueous Corrosion and its control course on NPTEL. Okay. So just some announcements. So we will have a doubt solving, no, a revision session kind of on 16th April. The time is not yet decided. Most probably it will be 8 a.m. to 10 a.m. to 12 a.m. But you will get a notification on the course announcement section regarding this. So on the revision session, we'll just cover all the. I won't be cover much of the theory because it will take too much time. But yeah, like most frequently asked questions on the assignments, I can go over those once again. Yeah, like mostly the calculation and few basic theories maybe we have time. Yeah. And there has been few announcements regarding the assignment grading. So, for example, uh, this is all mainly for those people who are applying for certificate for the course. So, assignment score is based. You'll have best three out of the first four assignments, and best three out of the next four assignments, 5 to 8. And the total assignment weightage is 25%, and weightage is for the final exam. There has been an announcement regarding that as well. Um, so this is regarding the exam format. Has the date been announced? Date hasn't been announced, but will be in April or May. I think toward the April and April or starting of May. And it will be offline pen and paper based exam from that situation. Uh, yeah. They did release a sample question paper last year. I hope they do the same this year. But anyways, I can discuss the last year's exam paper with you guys. Maybe in the revision class itself. And assignment 7 2. Oh, it's due tomorrow, right? So we can discuss. Let's have a look at the assignment question. I can go over some theory. It covers assignment questions actually. So okay. This assignment is basically on the interval corrosion and the de-alloying. Line attack. Before that, to understand the first question is about knife line attack occurs in which of those alloys. So I'll have to first discuss what is knife line attack. Okay. And then second, the presentation lecture. Let us first understand the knife line attack. Let's understand why we get granular corrosion first. Okay, intergranular corrosion or IGC. What's happening is let's take this. What's happening is we have our two grains, right? We have hexagonal grains, and so we're assuming case of stainless steel, 304 stainless steel, where we have 18% chromium, 8% nickel, and 0.8%, 0.08% carbon. So what happens here is mm, we have chromium in the bulk, right? Which the purpose here for chromium is to provide a passivation layer to prevent corrosion. Okay, and but what's happening here is at the grain boundary, uh, the carbon is reacting with the chromium, so carbon plus chromium, and is forming precipitates of chromium carbide. C6. There can be other stoichiometries as well, but yeah. So what's happening here is, and why is this precipitation happening at the grain boundaries? Because grain boundaries are like high energy sites where you have incomplete valency, so it's more chances of it's more thermodynamically stable to form precipitates, favorable to form precipitates. So what will happen is carbon will migrate toward the grain boundary, and so will chromium. So near the edge, close to the grain boundaries, you'll have depletion of chromium because it's migrating toward the grain boundary and forming precipitates at the grain boundary, forming a precipitate over here. Near this area, you'll have depleted chromium. So this depletion in chromium leads to you're losing the passivity which chromium was providing, and hence yeah, you get corrosion around the grains. Something if you have so eventually it's over time. There was this. This is a depth of attack. So at some at till here, till this top point, you are the chromium is leaching out of this area near the leaching out, so migrating out toward the grain boundary, forming a precipitate at the grain boundary, and after that, the precipitation has stopped because we have consumed uh, carbon around here, and yeah, so you saturated kind of the precipitation. Now what's happening is chromium from the bulk is moving, diffusing near those uh, precipitates, and again stabilizing it. So after a time, the depth of attack stabilizes, but you already have the corrosion has already happened, and yeah, you'll see in the microstructures, like corrosion happening around the precipitates. So how it relates to knife line attack. So next we have to understand what happens in weld decay. Again, this is related to the same phenomena, interkernel corrosion, but it's happening in welded metals. So if you know, like when you weld two metals, you're filling in hot metal, it will melt and join the two metals together, filling the area between them. And around this melted region, you get a heat affected zone. Okay, there will be some. It's not a hard boundary. It's a continuous zone, but the properties may have some limitations. Like, like suppose this is a plot. So this is your fusion zone. This welded zone is fusion zone. In the fusion zone, your metal completely melts, reaching suppose here 1800 degrees Celsius. And if you go further away, the temperature the highest temperature the metal would have attained would be lower, right? So at some point far away, it won't reach 450 degrees Celsius. It's below that, so nothing happens. Like nothing happens in sense related to well decay. Nothing happens. Okay. But once it reaches this 450 degrees Celsius, at that point, what happens is you start for carbide formation. Why do you need to have reach a certain uh, temperature? Again, to understand that, just go back to the slide. Like this, yeah. Your TTT plot was temperature, time, and transition. So at low temperature, you have limited diffusion of chromium toward the grain boundary, and you don't get that much of a like depletion of chromium near the grain. As you increase the temperature, the diffusion would increase, and this region would get more easily depleted. At certain temperature, you will get maximum depth of attack, right? Uh, this. If you go even further at higher temperature, what happens is the formation of these nucleation of this precipitate becomes thermodynamically unstable, and you don't form these precipitates. And again, you don't form precipitates, so the chromium doesn't uh, like get consumed and stays in the grain. Right? So at this region is around like the 400 to 850 degrees Celsius region. So they will depend on different alloys, but for this case, so once you reach 450 degrees Celsius, you'll start uh, forming this. precipitates. Okay, so that's far away, and near the fusion zone, what will happen is the chromium carbide precipitate CR23 C6. This is unstable above 1200 degrees Celsius. Above 1200 degrees Celsius, it dissolves. It dissolves. So we don't have precipitates at the main boundary, and we won't get IGC. Or again, when we reach the 850 degrees Celsius, when we are in between this range, 850 degrees Celsius and 450, we have maximum amount of precipitation of the chromium carbide. So we are forming chromium carbide, and that's the region where the temperature reaches this maximum region, where you will see maximum IGC attack. Okay, so this is what happens in weld decay. What happened? So now you know. Let's understand this plot. So this is was your TTT plot, time temperature transition, time temperature. Suppose if you start from here and you cool it very fast, you don't enter this region where the chromium carbide precipitation is forming. So no sensitization happens. So this is your chromium carbide formation region. Formation region. However, if your cooling rate is low enough, you cross this region and you form chromium carbide precipitates that will lead to IGC, sensitization of the sample. So what matters here is the time. You're starting from the same temperature, but you're using this at different times, right? You're spending how much time you spend in this region is important. So if you take the first case in the fusion zone, what will happen is you're crossing the 1200 degrees Celsius. Suppose this is the 1200 degrees Celsius. You're destroying all the, actually even of 850, you're destroying all the carbides. And once you reach this 850 degrees Celsius again, and you cool below 450 degrees Celsius, this is the range where your chromium carbide is forming. So you're spending this much time in this zone. So in the weld zone, you spend comparatively less time in the zone, so you don't form any chromium carbide precipitation since the cooling rate is high. However, if you see this plot, this blue one, you never reach the temperature above 850 degrees Celsius. So right when you cross the 450 degrees Celsius first time, the chromium carbide precipitation starts, and when you attain the like increase, the temperature increases and falls back during welding. Between those two times, so delta T HAZ, you're getting precipitation of the chromium carbide, so you get like, a lot more time. So the cooling is a lot slower, and you're spending much more time in this zone where chromium carbide is precipitating out. So here your sample is getting more sensitized toward IGC. So this happens particularly region where the temperature doesn't cross 850 degrees Celsius more. Doesn't cross the 850 degrees Celsius at the hot end. This will be the hot end, and is at least reaches 450 degrees Celsius. So there will be a region where you will get, again here you'll still have gradients, like close to this region will have a maximum amount of sensitization. As you move away, your sensitization will decrease. Similarly, this direction, the sensitization will decrease, but there will be a zone where you see maximum sensitization and maximum IGC happening. So now finally you can understand the knife edge corrosion, a knife edge attack. Knife line attack, sorry, line attack. What's happening? So to prevent this, what you can do is you IGC to prevent IGC. What you can do is add other carbide forming elements like titanium or molybdenum or niobium. NB. These will preferentially react with carbon forming carbide and thus prevent chromium. So the carbon is used up in titanium and niobium carbide precipitates, so you won't get chromium carbide precipitates. So this knife line attack happens only in the steels where you have some stabilizing elements. So tantalum, titanium, niobium, these are all stabilizing elements. So here what's happening is, yeah. So to reduce the heat affected zones, and if we have a thick sample, thick plates to weld, what we do is we weld the sample in multiple passes so the temperature doesn't increase that much, like very much. So we go and weld this in multiple passes each time, letting the weld cool down and then starting a new weld. So what happens is when you go through your first pass, what will happen? So you have inside your veins, you have titanium carbide and or tantalum carbide precipitates, right? PPT, precipitates. Okay. So right, so close to this fusion zone where you cross the temperature, so above like 1200 to 1400 degrees Celsius. Even these precipitates, which are more stable than chromium carbide, even they decompose and melt and degrade, and you get titanium and carbon. So they are separated. So that happens in the first pass, right? So you're this. This is your sample you're trying to weld, like sheets. So during the first pass, you weld this much area, suppose. So what will happen close to this fusion zone? You the area close to this zone reaches temperature above 1200 degrees Celsius. Okay, so if temperature is more than this causes decomposition of these carbides, and once it cools down, some precipitation would form, but yeah, here lost most of the carbides. Now in your second weld, like second pass, you're welding over here. Now this area is a bit further than the previous weld, so it won't go as high, and maybe it only reaches till 850 degrees Celsius. So now it's between that sweet spot for chromium carbide formation of 800 and 450 and 800 degrees Celsius. Since you're in that sweet spot, now in this region, during the second pass, leads to chromium carbide formation, 23 C6. So now you form chromium carbide precipitates. So that's consumed your chromium, which was providing passivity. So close to this region over here, you'll see attack corrosion, IGC corrosion, which we call knife line attack. So this was the first question. So hopefully I've explained the question, the answer, so you know what which one would be the correct answer. So in the lifeline knife line attack, you always have a stabilizing element present. So stabilizing grade stainless steel is a must. So yeah, based on this you can decide which other alloy. mm, Just Google each of these alloys and see which one has stabilizing elements added to it. Okay. Here the IEGC is the inclusion of austenitic steels would not occur. Here, let's go over the slide describing different steels. First, you have ferritic grade. Ferritic steels usually have higher carbon in fact. So, right, you have higher carbon, and if you have higher carbon, more carbon, this will react with the chromium, forming more carbide, and more chromium will leave your region around the grain boundary, forming another chromium carbon precipitate. So this will be your most susceptible. This is the most susceptible steel for toward integral corrosion IGC. Yeah, here the solubility of carbon is low. Again, uh, it doesn't want to stay in that CC structure, so it will move toward the grain boundary. So we usually add titanium or other stabilizing elements to prevent IGC. Austenitic steels, here the carbon content is low. The carbon content is low. Uh, but I think we didn't mention anything about diffusion. Mm, okay. So this carbon content is low, so lesser formation of chromium carbide. Typical better protection for aluminum. Third is martensitic. Martensitic steels. Here you have high carbon, but you know how martensite is formed. You quench it very fast. That leads to uniform formation of uh, carbides in the alpha. So inside the grain itself, you get uniform formation of carbides and carbides. That locks in your carbon and prevents formation of again chromium carbide at the grain level. So this is again less susceptible to IPC. So our question was austenitic steel would not occur. So if diffusion is high, so again, I think this was in duplex steel, right? Show the slide. Duplex steels. What happens in duplex steel, you have both alpha and gamma phase, so ferrite and austenite. So in alpha phase, your chromium diffuses much faster than gamma. So that's and in gamma phase you have higher chromium um, carbon diffusion. So what will happen? Your form precipitates, but since the diffusion from most of the chromium is coming from the alpha phase, and a relatively small amount of chromium is consumed uh, near the grain boundary due to this precipitation, right? So overall diffusion from the bulk compensates the region around the grain, the precipitate. So suppose this is your precipitate and this is your region around the precipitate where you had low chromium. So this is your chromium carbide. See, this right. CRC. So now what will happen is happening again. Still, this region, the rest of the grain is rich in carb, rich in uh, chromium, right? This is a small area. So what will happen from this chromium-rich region? Some of the chromium will diffuse toward this region, and this is your grain boundary. So just imagine this is the grain boundary, this region around that. So when this chromium diffuses to this region, again you have sufficient. This increases your chromium concentration, which again gives you the passivity due to chromium, thus stabilizing the ICC. Doesn't allow ICC. So if you have higher diffusion, you actually prevent intergranular corrosion. Okay. Chromium content. So chromium content doesn't matter since near the grain boundary, even if you increase the chromium initial chromium concentration, you'll still deplete chromium due to formation of carbide. So you'll still get chromium carbide. Doesn't have help much. Chromium carbide not present in the grain boundary, it doesn't matter. Like if chromium carbide is not present, it will migrate and form chromium carbide. Chromium depletion does not occur at grain boundary. Yeah, so chromium depletion is the reason we are losing the passivity and thus causing IGC. So if we stop the depletion, you will stop the IGC. Okay. Mhm. What does sensitization depend on? So factors controlling sensitization. So mainly the carbon content and type of grain boundary, right? High energy or low energy, high or low angle grain boundary, which has high or low energy. And sorry. Mm. Grain size also affects IGC. So your carbon content affects it. And grain boundary is affected. If you have uh, high energy grain boundary, it will have more nucleation, easier nucleation. Okay. So this low angle grain boundary is also called twin boundary. The twin boundary has will take longer time and it will take longer to sensitize the steel for IGC. And yeah, carbon getter or your stabilizing elements, they also affect your sensitization. Okay. Well decay. Well decay. Found it here. Well decay. So here we are adding stabilizing like in the knife line attack we have stabilizing elements, but still we're getting IGC attack in this region. Solutionizing heat treatment. Question. Prevention of well decay not possible. Okay, okay, okay. It's inverse. So yeah, adding some stabilizing element will prevent well decay. Increasing carbon content does shouldn't affect, right? The well decay is happening due to the time it spends there. So if you remember this plot, it's, your sensitization. Uh, if you have higher carbon content, this is highest carbon content. And as you're moving this way, this is lower, this is lowest carbon content. This is where this one is the most susceptible to IGC. So this would still apply in this well decay. Increasing carbon content would not help. Really. Type of surface treatment. Effect of cold work. So low level cold work increases IGC. This location can easily transport carbon. And if you have high level cold work, that actually reduces IGC. And because it promotes your chromium carbide precipitation inside your uh, grain instead of the grain boundary. So the following statement is true for intergranular corrosion of stainless steel having similar carbon content. Similar carbon content, now you have to judge by diffusion of carbon. Yeah. Ferritic, yeah, we already discussed this. Ferritic is more susceptible, austenitic is lesser, or means, yeah, this is the least one, and martensite still less susceptible, but somewhere in between these two. PMF. But yeah, duplex steel, here you have even less susceptibility, is more resistant than ferrite and austenite both. Yeah, duplex is yeah least susceptible. The most would be a ferrite and least is duplex. And these two are in between. So the order would be something like right. Inside, I think still like debatable or equal. Triple, stenite, and we still reflex. Which of the following suffers IGC when welded? So here I think what will matter is this plot. In your first pass, you're going, if you're retreating it above 1200 degrees Celsius, you're destroying the chromium carbide. But why is the first answer not? So the 321 SS and 304 SS, when they're exposed to high temperature, they become sensitized. And when we quench them, that leads to precipitate carbide precipitation. Whereas in 304 LSS, we have low carbon, and yeah, with proper heat treatment, you're preventing uh, carbide formation. So there's they have low carbon. I think that must be the main reason they are suffering more IEC. Resistance to erosion corrosion. See what is in the order. Erosion corrosion occurs due to mechanical wear in flowing seawater, right? So Monel is nickel copper alloy. I still haven't watched all the videos, but if you can Google it, question. So Monel is nickel copper alloy. This has highest resistance to erosion, corrosion, and alpha phase is the weakest. We can form the intermediate steps. I think this is must be covered in the lecture. Anyways, if you Google it, you can find nonsense. De-alloying. Highest de-alloying expected which of the alloys? highest DA line, so whichever is the most active metal in these, I think you can refer to the activity series, like which is the most reactive metal, then copper. So that will be the most highest susceptible to a DA line. For example, like I think let's check electrochemical series. So, yeah. So zinc is more reactive than nickel. So nickel तो definitely नहीं है, and we'll have to check where aluminum and, and copper. Let's refer to the electrochemical theory, which is the most reactive would have the highest DA line. So like DA line, what is happening in DA line? So you have your sample which has both copper and suppose zinc, copper and zinc. When it's exposed to the environment, your zinc atoms would leach out zinc plus 2, and your solution has some copper plus 2. So this zinc would give its electron to this copper, and so a copper would get deposited somewhere, and zinc would leave, forming pits on the surface. So if it's suppose it was nickel compared to zinc, nickel is less reactive than zinc, so you'd expect less than. Let's refer to electrochemical theory, like which is more noble. Copper is nobler than zinc, so it's taking electron from it. Nickel is comparatively less noble, more noble than zinc, so it will have lesser tendency to give electron to zinc, to copper. Sorry. So I think aluminum is the most reactive, so aluminum is the most the easiest which will give the electron to copper. Which are the following statements for the line? In must be provided by exercise. Only partial haven't completed this lecture for the 10 minutes. But so high temperature would increase diffusion. Yeah, so but if you increase the electrolyte temperature, your diffusion would increase. Then I think it should increase the DA line. If more active, active element content is increased. If again the allowing increases, I think that was related to also related to percolation, where if you have sufficient like percolation theory was like you have copper atom sitting on the surface. If you even this is a surface, so if you have copper sitting here, if you have low copper concentration, sorry, copper zinc concentration, once these zinc ions leave, the next zinc ions are too far away, zinc atoms are too far away, and they won't react. They form a continuous channel, like at least some of the zinc is zincs are connected, like there will be copper in between. Once this one leaves, the next one there's a channel here for the next one to leave, so next one would leave, and so will form like a long channel inside the sample. This is percolation theory again. In aggressive environment, yeah, your DLI should increase. So if you lower the pH, increase the Cl minus concentration, promote DLI. And increasing the potential also increases DLI. Yes, one should be fine. Which of the following statement is true for flow state assisted corrosion? So flow assisted corrosion occurs in low oxygen environment where protective oxide layer dissolves, so you don't have passive layer formation. If you inject oxygen, it's forming a protective iron oxide layer and radiation corrosion. Higher chromium content reduces again higher chromium content would increase your passivity and actually should reduce flow assisted corrosion. And flow assisted corrosion does not increase linearly with temperature. That would be incorrect as well. I think this was covered in the lecture, and anyway, we'll discuss situation next week. Okay. Again, since there was no one at the beginning of the class, marking scheme and the exam has been announced. It will be a offline pen and paper exam. The date will be released probably toward end of April or beginning May. Okay. And the exam would have 75% weightage, and your all your assignments will be 25%. We'll have best of three assignments in the first four, and again best of three will be taken in the next four last four assignments. If they release the sample question paper, we can discuss it, or I think they have the last Previous year there is a sample question paper well discussed during revision session. Okay, yeah, I'll post the recording session today.
Another one more question from my side.
Yeah,
Paper given that it is a paper and pen exam.
yeah.
So means it is like a same assignment type questions or have to write essay type questions.
Uh, the questions would be like, I think, similar to assignment, but there you'll have to justify everything and write detailed steps.
Okay.
Yeah.
Means not ABCD. You have to write
No, no,
answer.
no. I don't think it will be objective type. It will be subjective.
Okay.
So let me see if I have. Let me share the screen. So this was from last year. So example solution of the question. So you can see it is subjective questions. A lot of them are calculation based. I'm not sure if this is the actual question paper from last year or just a sample question. But yeah, expect something similar to this. Okay.
Means 50% problematic, 50% theory, isn't it?
Uh, problematic, you mean numericals, like
Numericals 50%,
numerical, yeah, yeah.
50% theory.
Maybe, I
Maybe.
think.
Okay, right, right.
I'm not sure. Okay. You can also post in uh, the FNQ question and answer section. The other TA, she is supposed to be handling the assignment, forming the assignment and forming the question paper for the examination, maybe. Or maybe she is actually a student of Professor Raja, so she would have more uh, like accurate answer regarding.
Okay, okay, sure, sure.
Yeah, yeah. Okay. Okay. Anything else? I think we can end
I
the
have a
session here.
doubt in stabilization. What is the meaning of stabilization? Means formation of ally or de-allying?
Stabilization. Are you talking about some assignment question? Yeah, I say in general,
Discussing assignment,
similar.
talking about stabilization, destabilization. What is the
Okay.
meaning? Stabilization means formation of ally.
Stabilization, I mean, I
You are
think.
adding titanium, thallium, etc. For
Oh,
stabilization
yes,
means
yes,
they
yes,
are
yes,
forming
yes.
ally.
So you're talking about stabilizing. So let me just grab the slide. I think
Mm,
factors affecting
stabilization.
stabilization. So like this adding getters. Research. So adding titanium, niobium, tantalum, this is stabilizing the steel. So it's stabilizing by forming titanium carbide. So your carbon is reacting with these uh, stabilizing elements instead of chromium. So your chromium provides your passivity. So since your if the carbon was free to react with the chromium, it will form chromium carbide and it will consume your chromium from the region around the precipitate and you lose your passivity. So to counteract that, we are adding titanium, these stabilizing elements. These will consume the carbon, thus reducing, and thus your chromium is not consumed and you maintain your passivity.
Okay, correct. To maintain the passivity, we are removing the
Carbon.
unstabilizing compound.
So we
Okay,
are removing carbon. So by adding other carbide forming elements. So chromium carbide is not forming. Instead, these other carbides are forming.
okay, correct, correct.
Okay. Yeah, tomorrow is deadline for the assignment. I'll upload this session right after the class. Okay. So if you don't have any other doubt, we can end. Okay. Thank you for attending. See you
Thank you.
next week.
Thank you.
Bye bye.